Hi dears, welcome to my channel. Today we are discussing 9th standard 11th lesson, that is sound. What was the 10th lesson? It was work and energy. There we learned about the different types of energies and the relationship between the power and energy and many other things. And at the end of the class, I have asked you 3 questions. Do you remember? It's the time to answer these questions. The first question was, the rock rolling from the hill possesses which kind of energy? The rock which has started to roll and now it's rolling down. Which kind of energy does it possess? It possesses kinetic energy. Then, second question, what kind of energy transformation is occurring in a thermal power station? Thermal power station is the one which converts heat energy into electrical energy. So, this is the answer. Third one is, what kind of energy does an arrow in a bent bow possess? The arrow is still in rest even though it is in bent bow. So, which kind of energy does it possess? It possesses potential energy. Now we are learning about sound. I have parted the lesson into 2. Here, this is part A. In this, we are discussing what is sound, how is sound produced, how is the sound propagated, then the mechanical wave nature of the sound, longitudinal characteristic of the sound, then what are the characteristics of sound, then about the reflection of sound. Third, we learn about echoes and reverberation. Up to this extent, we will learn in this chapter. Okay. First, what is sound? What is sound? Sound is something that we hear and can be heard, isn't it? Or we can say sound is a source of energy which helps for the communication. So, we should know how is the sound produced. Now, I am having 2 things with me, a bowl and a scale. Okay. If the bowl is moving like this, will it make sound? No. If the scale is moving like this, will it make sound? No. If I am stucking the scale on the bowl, see, sound is produced. Here, when I am touching the scale on the bowl, vibration of the particle occurs. Vibration results in making sound. Here, in the case of humans, when I am talking with you, my vocal cord is vibrating, which makes the sound. Okay. When in the case of bees, buzzing sound, have you heard? For the crickets and grasshoppers, when they are rubbing their wings together, sound is produced, isn't it? And for the birds, when they are flying in the air, when they are flapping their wings, sound will be produced. So, vibration of particles is needed. In every cases, in one way or by other way, due to vibrations, sound is produced. Okay. Now, the next question is arising. That is, how this sound is heard by us. Some objects are making sound, but we are able to hear it, isn't it? So, how does the sound is moving? We have to know how the propagation of sound is occurring. For the propagation of sound, 3 things are needed. Source, a medium and a listener. Okay. Source, we know. That is, who produces sound is the source all the time. Okay. We have discussed it earlier. Now, the second is, it has to be traveled. By which it is traveling. The sound always need a medium to travel, which you have already learned from smaller classes that sound requires a medium to travel. So, without a medium, the sound is not able to travel. Okay, through the medium, the sound is traveling and to our ears it is reaching. Then only we will be able to hear the sound. So, how is the sound traveling? Consider this as the speaker, loudspeaker, and it is making sound. And consider this as the medium, air. And this is your ear on which the sound has to be heard. How is it moving? We will see. This is air. So what happens is, in the loudspeaker there is a membrane which vibrates to make the sound. Okay. So from the membrane, due to vibration, sound energy or sound waves are produced. Then what happens? The sound waves enter into the medium, and in the medium air there are particles, isn't it? We all know that the matter is made of particles. Even though it is air, or even though it is water, or even though it is solids, that particles are there. So it just makes that particle in the air to move. To move means to vibrate from its equilibrium position. Actually, the particles of the air are in equilibrium position, and when I am stucking it with a force, what happens? It will move to and fro. So, in the medium air, the particles of air starts to move to and fro. So, what happens? This sound waves also passes. The sound waves are a kind of pressure waves which makes the particles of the air to move to and fro, to and fro, to and fro, like that it starts to move. Sometimes the pressure wave will be much more higher to make that air particle to compress. So this is the compression area. Then what happens? Then the pressure wave will be a little lighter, so the particles will be back to the position. So this results in the rarefaction. Then they will pull against, makes the compression, and then they will release, makes the rarefaction. Compression, rarefaction, compression, rarefaction. So the air particles starts to move to and fro from the equilibrium position, makes themselves in a compressed manner and makes themselves in a relaxed manner. When they are in the compressed manner, the pressure will be maximum. Okay, when they are in the relaxed manner, pressure will be minimum. So maximum pressure, minimum pressure, maximum pressure, minimum pressure. In that manner, the particles will be vibrating from their equilibrium position. So if they are getting the sound energy, they will vibrate and they give that energy to the next particle. That particle also starts to vibrate. Then the energy will be given to the third particle. Then like that, the sound energy will be moved forward. Is the particles of the medium moving? No. They are just vibrating from the mean position as to and fro. So, by that manner, what happens? By that manner, the sound energy is moving. And at the end, it is reaching to your ears. So, we can say, if the medium is not there, is the sound able to move? No. So, we can say only by the presence of physical medium, the sound energy is able to move. So, we can say the sound energy is having mechanical wave nature. A sound wave is a mechanical wave. That means it needs a physical medium for the movement, for the further movement of the sound waves. So sound wave is a mechanical wave and it is not electromagnetic wave. Light is an electromagnetic wave. That means light can travel through vacuum. Is it possible for the sound? No. Sound needs a medium. That's why in vacuum, through vacuum, the sound can't move. Okay. The sound wave is a mechanical wave. Is it clear now? The particles of the sound is moving to and fro manner. That direction is same as that of the propagation of the wave. The particles are moving to and fro manner, then giving it to the next particle, then they are moving to and fro manner, then giving to the next particle, then it is moving in to and fro manner. In the same manner, the sound waves are also traveling. So these two are parallel to each other. So we can say that sound waves are longitudinal waves. If the sound waves are transverse wave, the particles of the medium will be traveling in the direction which is perpendicular to the direction of propagation of wave. But here, the particles of the medium are moving parallel to the direction of propagation of wave. So we can say that the sound is longitudinal wave and it is not a transverse wave. Now, if we are expressing the wave, sound wave in the form of a graph, it will be coming in this manner. That when the sound is produced, when we are saying this part as density, if the sound is not produced, it will be in the equilibrium position. But as the sound waves are traveled, because of the compressed area, it makes a compression, results in the formation of a crust over the rarefacted area, shows a trough, and again crust, again trough, again crust, again trough, again crust, like that. The waves will be traveling. So, the area where the compression is maximum is said to be the top part, or which is called the crust, C-R-E-S-T, and the place where rarefaction is maximum is said to be trough. So this is the graphical representation of the sound waves. Now we are saying about the characteristics of the sound waves. What are the specialities of the sound waves? These waves are having particular characteristics. Here we can say the maximum height or maximum displacement from the mean position. This is the mean position and the sound waves makes the maximum displacement. Here as well as here, the same displacement will make for rarefaction also. So the maximum displacement is said to be the amplitude. What we are saying? Amplitude of the sound. What is amplitude? The maximum displacement from the mean position of the sound wave is said to be amplitude. Sound. What does the amplitude depends on? The amplitude depends on the force in which we are applying. If I am saying students keep quiet, not much force I am applying on it. So the amplitude also will be very less. But if I am saying students keep quiet, the force in which I am making sound is more, isn't it? So loudness is also increased. This loudness depends on what, ma? Amplitude. Okay, did you get the difference? So how will be the graph? First, if I am making a soft sound, this will be the graph of amplitude, and if I am making a shrill sound, the amplitude will be getting increased, and this will be the graph. Okay, did you get the difference? Okay, now second one is about the frequency of the sound. What is frequency? Frequency is the number of oscillations that the sound waves makes in 1 second. So they have given the time. Within 1 second, how many oscillations does the sound wave makes? This makes the frequency. Okay, ma? So how can you understand the frequency is changed? Pitch of the sound depends on frequency. How can you understand that? See, I am having a steel mug and I am having a plastic item with me, and I am having a spoon with me. Okay, if I am striking, you will be able to identify whether the pitch is greater in which and pitch is less in which. Okay, ma? Here the steel spoon is striking on the plastic. Okay, have you heard the sound? Now it is striking on the steel item. Have you heard? Now the same force I am applying on this spoon and the same energy which I am adding on both the items, but still the sound is different. Yes, the sound is different. This shows that pitch is different for different items. See here for the plastic, this is the maximum pitch, and what about the steel item? This is the maximum pitch. So what we are saying is the pitch of the sound depends on the frequency. So how will be the frequency for the first item in which we are rubbing? If we are striking with the plastic, it will be like this. Okay, what about the steel item? Did you get, ma? So for the plastic, this is the pitch, and for the steel, this is the pitch, isn't it? If the number of oscillations are more in 1 second, we can say that frequency also is larger. Okay, frequency is having the unit hertz. You have all learned in the 8th standard itself, right? Humans can hear the sound from 20 hertz to 20,000 hertz. Below the 20 hertz, we are not able to hear, and we are saying it as infrasonic sounds, and above 20 kilohertz, we are not able to hear that also. We are saying it as ultrasonic sounds. Okay, so this is the frequency range of human ears. Now we are moving to see the third one, that is wavelength of the sound. What is wavelength, ma? Wavelength is the distance between two consecutive crusts or two consecutive troughs. Okay, so wavelength is the distance between, consider this as the crust. From the half I am taking, and then this is the half. So up to this extent to this extent, we are saying it as wavelength. Okay, so if the frequency is more, in that how will be the wavelength? Wavelength will be less, isn't it? If I am using the steel spoon for striking the steel vessel, what happens? Frequency will be more, isn't it? So what will be the wavelength? This will be the wavelength. If the same I am doing with the plastic, what will be the frequency? Frequency will be like this, isn't it? So this wavelength will be what, ma? Wavelength will be more. So if the frequency is getting increased, what will be the wavelength? Wavelength will be decreasing. Frequency and wavelength are always inversely proportional to each other. Okay. So in the case of sound, frequency of the sound and wavelength are inversely proportional. Okay. Yet another one which we have to know is time period. Time period is time taken for completing one oscillation. Here the oscillation is fixed, and they are asking what is the time taken for that. There in the case of frequency, the time period was fixed, and they are asking how many oscillations they have gone. Okay, ma? So this time period is inversely proportional to, or time period is exactly opposite to the frequency. So we can define time period as time period is equal to 1 by frequency. Okay, what is the unit of frequency? Hertz, I said. And how we can represent the frequency? Frequency can be represented by the letter nu, isn't it? And what about the wavelength? Wavelength can be represented by lambda. Okay, so how can we represent the time period and frequency relation? Time period is equal to 1 by nu. That is, time period is inversely proportional to frequency. Okay. Now, the last characteristic of the sound wave is about the speed of the sound. Speed of the sound is the product of frequency as well as the wavelength of the sound. Speed of the sound is a product of what, ma? Frequency of the sound and its wavelength. Okay. So what does the speed of the sound depends on? Speed of the sound mainly depends on the material medium. As in the case of solids, the particles are closely packed. The speed of the sound also will be maximum for the solids. Then it will be for the liquids and lastly for the gases. The speed of the sound is maximum for what, ma? For the solids. Okay, in the case of aluminium, if we are allowing the sound to travel through aluminium, the sound will be traveling at the speed of 6,420 meters per second. So, in the case of air, the speed of the sound will be only 344 meters per second. Okay. From these two data, we can analyze how much the speed of the sound varies in the case of solids as well as in the case of gases. Okay. So the speed of the sound is also a matter and it is the product of frequency and the wavelength. Dears, yet another important topic about sound is the reflection of sound. Do the sound reflect? Yes. Like light, sound also reflects. The sound is hitting in any hard surface, it reflects that sound. The hard surface reflects the sound. If the sound wave is hitting on any soft objects, it absorbs the sound while the hard substances reflect the sound. So, as the light, sound also reflects and it will be having angle of incidence and angle of reflection. If we are considering a plane and if the sound is traveling in this direction, we are saying it as incident wave of sound. Then it will be striking that surface and it will be reflected back in another angle. Okay, ma? If we are drawing a normal, like light, we can say angle of incidence of the sound is equal to angle of reflection. This is the law of reflection of light we have seen. Na? In the law of reflection of light, they said angle of incidence is equal to angle of reflection. The same will be followed for sound also. Angle of incidence is equal to angle of reflection. What was the second law of light? Second law states that angle of incidence and angle of reflection and the normal all should lie in same plane. Was the second law, right? The same thing for here also. The incident wave, the reflected wave and the normal should lie in the same plane. Then only the refraction will be proper for the sound. Okay. Because of the reflection of sound, something is happening. Have you heard about the echoes? What is echoes? When we are making a sound, after a little time gap, the same sound of us will be heard back to our ears, isn't it? This is echo. The echoes are formed by the reflection of sound. When you are in the top of a mountain and if you are making a sound with a high voice, after a particular time delay, we can hear our sound back. We are saying it as echoes. So, we have to understand one thing. What is that? That is, for hearing the echo, there should not be an obstacle nearby. Obstacle should not be nearby. That's why in the mountain tops, echoes are heard. Otherwise, in our room, can we hear echoes? No. But in the mountain tops, we are able to hear. Means what? In the mountain tops, there is no much obstacle other than the other mountain, which is far away, isn't it? So, echoes are heard if the obstacles are at large distance. Okay, ma? Produced. Now, we are going in detail how the echoes are produced. Actually, what the specialty of our brain is, our brain can persist our sound for 0.1 seconds. Whatever we are saying in our brain, it will be persisting for 0.1 second. Okay, if we are making a sound and if it is reflecting back after this 0.1 second, we will hear our same sound as an echo. Is it clear now? That's it. If we are in the mountain top, okay, ma'am? If the person is in the mountain top and if he is talking something, if he is shrilling something, and if there is a mountain, it should go and it should reflect back to his ears, isn't it? If it is coming after this 0.1 second, he will be able to hear his sound again as an echo. Now, one more question is arising. How much distance the sound waves have to travel to be heard as an echo? How much distance the sound wave has to travel? we have seen already that air is the one which takes the sound in very less speed, because in the air particles are not closely packed. That's why air takes the sound very less speed. Normally, the air takes the sound at the speed of 344 meter per second. Okay, so 344 meter per second is the speed of the sound in air. Now you have to listen carefully. The persistence of the sound for the brain is what, ma? 0.1 second. If we are dividing it with 0.1, we will get the answer as what, ma? 34.4. You are experts in mathematics, so I need not explain how you are getting 34.4. Because if we are dividing this, we will get the answer as 34.4 meter. So this 34.4 meter is the minimum distance the sound wave has to travel to reach to our ears as an echo. Okay, this is the minimum distance the sound has to cover. If there is any obstacles in between, will it travel to that distance? No. So we are not hearing the proper sound as echo. But when we are on the mountain top, this much distance if it is covering, we will hear our sound as echo. Now 34.4 are again divided into 2. We are dividing 34.4 by 2. So we will get 17.2. Why did I divide it? Why should I divide it by 2? The reason is, if the sound is moving to a distance and if it is hitting, it will reflect back. So half distance if the sound is traveling, then also we will be able to hear the echo. Okay, going sound 17.2 and coming back sound 17.2. Okay, if it is moving to a 17.2 meter and if it is reflecting back after by 17.2 meter, we will be hearing after 0.1 second. Then it will be distinct as echo. Did you get how the echo is heard? So 17.2 meter, the sound waves should travel without any obstacle, and it should be a hard substance, and that obstacle should reflect that sound, and again 17.2 meter the sound, reflected sound has to travel, and it should be heard after 0.1 second. Then only we can hear a clear echo. Okay, is it clear? Sometimes the echoes will be heard again and again. Again and again and again. Sometimes echoes will be heard. The reason is simple, ma. Repeated reflection of the sound will be produced. One times it will be coming back, again it will be going and coming back, again it will be going and coming back. If we are producing such a hard sound, that sound waves will be reflected again and again and again, till the sound waves has no strength to travel. To that extent it will be reflected back. So again repeatedly we will be able to hear the echoes. Now we are going to yet another part, that is reverberation of sound. Even though echoes are not very much familiar for you, reverberation will be much more familiar. Reverberation is the one when you are entering into a hall which is under construction, and if you are making a sound, that sound will be heard again and again, but that sound will not be clearly heard. Again and again the sound will be repeated, but it will not be clearly heard. What is this? This is the reverberation of sound. What the problem happens here is, the sound is reflecting back there also. Here also the sound is reflecting back, but the time gap is very small. It is below 0.1 second. Below 0.1 second, if the sound is hearing back, already the brain is persisting our sound. Again one more sound is coming. Then again one more sound is coming. It will be reflected again and again. So what? Overlapping of the sound happens. So whatever we have talked, that thing will not be properly clear for us. That is reverberation of sound. It was a main villain in cinema halls in the earlier times. The cinema hall was very big, isn't it? Cinema hall now also is very big. So in that cinema hall, if a sound is produced from the cinemas, that sound, because of the reverberation, the audience were not properly able to hear the sound, not able to catch the sound properly. Okay, so this reverberation can be avoided by using sound absorbing substances. Some sound absorbing materials are there. So what will they do is, in the cinema hall, they will keep the sound absorbing substances in the ceilings or in the top of the wall, and also that the sound will be, that items will be much more softer. So they will grasp the sound. Reflection will not be produced again. So the sound will be clear. Okay, the things clear about the echo and the reverberation. part A is completed here. Rest of the class will be seen in the part B on the next section. Bye.